Hello everyone, we continue chapter 10 by starting section 10.3 matrix representations of graphs. So far we have represented a graph either using graphical tools or using set roster notation and edge endpoint functions, but here we are going to represent a graph using a matrix called adjacency matrix of that graph. In order to define the adjacency matrix, we first need to define a matrix in a mathematical way. So here is a formal definition of a matrix. We say an m by n matrix A over a set S is a rectangular array of elements of S arranged into m rows and n columns. So basically A, which is a matrix, is represented by this rectangular array inside two large brackets, and inside these brackets we have m rows and n columns. In the first column you see the elements a1, a2, a11, a sub 21, a sub all the way to a sub I1, all the way to a sub m1. And then in the second column we have a1 to a2 to all the way to a m2. And in the last column we have a1n, a2n, all the way to a mn. So as you see, the subscript of each element, like a1j, has two integers, 1 and j. 1, which is the first subscript, shows the number of row that this element is in, and j, which is the second integer of the subscript, shows the number of column that this element is. So we can shorten this representation of a matrix and write it in this way. We say A is equal to aij in parentheses subscript m times n. So m times n shows the size of the matrix, it means that this matrix has m rows and n columns. This is the ith row of a matrix like A. In this row we have n elements, ai1, ai2, all the way to ain, and this is the jth column, a1j, a2j, all the way to amj. And here we define the adjacency matrix for a directed graph. We say if G is a directed graph and there is an order for the set of vertices of the graph, like v1, v2, all the way to vn, then the adjacency matrix of graph G is an n by n matrix like this. A is equal to, in parentheses, aij, n by n, which shows the size of the graph, size of the matrix, over the set of non-negative integers. Okay, so all the elements of this matrix should be integers that are either positive or zero, such that aij is the number of arrows from vi to vj for all I and j from 1 to n. So since we have a directed graph, a sub ij counts the number of arrows starting from v1 ending at vj, correct? So in order to illustrate the concept of adjacency matrix, consider these two graphs, graph A and graph B, and let's see how we can represent these two graphs using adjacency matrix. For the first part, for part A, Since the graph has three vertices, v1, v2, and v3, so we have a 3 by 3 adjacency matrix for this graph. This 3 by 3 matrix has 9 different elements. In the first element in the first row and first column, this element counts the number of arrows from v1 to v1, from v1 to v1. So as you see, there is no edge connecting v1 to itself. So here we need to put 0. For the second one, the second element in the first row, we have the number of arrows connecting v1 to v2. So as you see, there is no arrow from v1 to v2, right? And here again, the third element of the first row is 0 because there is no arrow from v1 to v3. You see, this is v1, this is v3. There are two arrows from v3 to v1, but there is no arrow from v1 to v3 in the opposite direction. And let's see what happens in the second row. In the second row, we need to count the number of arrows starting at v2 and ending at either v1, v2, and v3. There is no arrow ending at v1. As you see, there is no arrow starting from v2 and ending at v1, but there is one arrow from v2 to itself. It's e5 that starts and ends at the same vertex v2. So here we put 1, and there is also one arrow starting at v2 and ending at v3, this arrow called e3. And in the third row of this adjacency matrix, we have numbers 2, 1, 0. Why? Because there are two different arrows from v3 to v1. As you see, there are two parallel edges connecting v3 to v1. There is only one arrow from v3 to v2. It's called arrow e4, and there is no loop on v3, so there is no arrow from v3 to itself, so that's why we put 0 here. In a similar manner, you can pause this video and see if you can obtain this adjacency matrix for the visual representation of graph shown here. Then we can have the similar definition that we had for adjacency matrix of a directed graph, this time for an undirected graph. Let G be an undirected graph with an ordered vertices v1, v2 all the way to vn. The adjacency matrix of graph G is an n by n matrix like this, A equal to, in parentheses, Aij, n by n, over the set of non-negative integers such that Aij is equal to the number of edges connecting vi and vj for all I and j from 1 to n, right? So this time Aij represent the number of edges connecting vi to vj, but in the directed graph the Aij was the number of arrows starting from vi and ending at vj. Okay, so we continue chapter 10 by starting section 10.4, isomorphisms of graphs. Before defining the concept of isomorphism in a formal way, I'm going to show you two graphical representations of two graphs. The first one is here. As you see, we have a graph with 5 vertices and 5 edges. And the second one is here. Again, here we have 5 vertices and 5 edges. as you see in this graph, vertex 1 is connected to vertex 2, vertex 2 is connected to vertex 3, vertex 3 is connected to vertex 4, vertex 4 is connected to vertex 5, and vertex 5 is connected to vertex 1. In the similar way, here we can also say 1 is connected to 2, 2 is connected to 3, 3 to 4, 4 is 4 to 5, and 5 to 1. So these two graphs have the same number of vertices, have the same number of edges, and have the same connectivity pattern, right? So in order to formalize the same notion that we are talking about between two graphs, we define the concept of isomorphism in the following way. We say let G and G prime be two graphs with vertex sets V of G and V of G prime, and edge sets E of G and E of G prime, respectively. So V of G and E of G are vertex and edge sets for graph G, and V of G prime and E of G prime are vertex and edge sets for G prime. We say G is isomorphic to G prime if and only if there exist one-to-one correspondences G from V of G to V of G prime, and H from E of G to E of G prime that preserve the edge endpoint functions of G and G prime, in the sense that for every vertex V belongs to V of G and edge E belongs to E of G, V is an endpoint of E if and only if G of V is an endpoint of H of E. So let's take a second look at this definition. In this definition, we say G is isomorphic to G prime if there exists two one-to-one correspondences, one G, the other is H. As you remember, one-to-one correspondence is a one-to-one and onto function. So in this definition, both G and H are one-to-one and onto functions that preserve the edge endpoint functions of G and G prime. What does this preservation mean? In order to define this preservation, we have this condition. We say for every vertex V belongs to the vertex set of G and edge E belongs to the edge set of G, V is an endpoint of E if and only if G of V is an endpoint of H of E. So let's see how we can prove that these two graphs are isomorphic to each other. I'm going to prove that G is isomorphic to G prime. That's why I need to construct two functions, two one-to-one and onto functions, or two one-to-one correspondences, one like G from the vertex set of G to vertex set of G prime, the other like H from the H set of G to H set of G prime. So that's how I create this one-to-one correspondence. First of all, I say V1 is mapped to VW2 in graph G prime. As you see, this is the arrow that represents this correspondence. In a similar way, I can say that V2 corresponds to W3 and V5 corresponds to W4, correct? And we have two more vertices left, V3 and V4. V3 corresponds to W1, V4 corresponds to W5. So I created a one-to-one correspondence between the vertex set of G and vertex set of G prime. And based on the correspondence that we created for the vertex sets, we can create another correspondence, another one-to-one correspondence like H for the edge sets of G and G prime, but we need to be careful to define H in a way that correspondences G and H, they both preserve the edge endpoint functions of G and G prime. It means that if V and E are two vertex and edges of graph G, V is an endpoint of E if and only if G of V is an endpoint of H of E. That's why, for example, if you look at E1, which connects V3 to V1, should correspond to F3 here. Let me show it with red ink. These two should E1 should correspond to F3. The reason is that E1 connects V1 to V3 in graph G, so F3 also connects connects W2, which was corresponding to V1, to W1, which corresponds to V3 in graph G. So E1 corresponds to F3 because the endpoints of E1, which are V1 and V3, are corresponding to W2 and W1. In the same way, you can create other correspondence relations between all the elements of E of G to all elements of E of G prime. And after creating this correspondence, you can claim that based on the definition of isomorphism of graphs, graph G is isomorphic to graph G prime. Okay, so here we see a very interesting theorem 1041, which is about graph isomorphism. It basically says if S be a set of graphs, a set of all graphs, and R be a relation of graph isomorphism defined on set S, then R is an equivalence relation on set S. So basically, this theorem claims that graph isomorphism is an equivalence relation. You can prove this by proving that graph isomorphism is reflexive. It means that every graph is isomorphic to itself. It is symmetric. It means that if G is isomorphic to G prime, then G prime is also isomorphic to G. And also, this, graph isomorphism is transitive, which means that if G, which is a graph, is isomorphic to another graph like G prime, and G prime is isomorphic to another graph like G double prime, then we can conclude that G is isomorphic to G double prime. Okay, so the proof of this theorem is very straightforward. You can take a look at the book or try yourself to prove theorem 1041. But here I'm going to show you an example that illustrates the application of theorem 1041. Example 1042, which is about finding representatives of isomorphism classes. As you know, since graph isomorphism is an equivalence relation, and every equivalence relation defines a set of equivalence classes. here we have also some equivalence classes for isomorphism called isomorphism classes. And also we know that an equivalence class on a set like S partitions that set using its equivalence classes. As a result, R, which is an equivalence relation on the set of all graphs S, also partitions S into its equivalence classes. So in example 10.4.2, we only focuses on graphs. We only focus on graphs that have two vertices and two edges. Okay, we are going to say the isomorphism relation will partition all the graphs with two vertices and two edges into four different partitions. And the question in example 10.4.2 is to find all non-isomorphic graphs that have two vertices and two edges. When you find all non-isomorphic graphs that have two vertices and two edges, you have basically found the representatives of isomorphism classes. I'll explain more later. Consider these four graphs. As you see, every two graphs that you pick from these four graphs are non-isomorphic. None of them are isomorphic to another one. Okay, so you can disprove the isomorphism relation between all of these A, B, C, and D graphs by pausing this video and checking yourself. But after making sure that none of these graphs are isomorphic to another, then you can claim that any other graph that you draw with two vertices and two edges is isomorphic to one of these four graphs. The reason is that these four graphs are non-isomorphic, so each one belongs to a different isomorphism class, and since there is no other non-isomorphic graph with two vertices and two edges, we can claim that we have only four distinct isomorphism classes for the set of all graphs with two vertices and two edges, and we can consider these four graphs as representatives of the four distinct isomorphism classes that we have for the set of all graphs with two vertices and two edges. The final definition that we present in this lecture is the definition of a graph, the definition of a tree and a forest. We say a graph is said to be circuit-free if and only if it has no circuits. Okay, what was the definition of a circuit? A circuit is a closed walk that contains no repeated edge. A graph is called a tree if and only if it is circuit-free and connected. So a tree is a graph with two restricting conditions. First, it should be circuit-free, and second, it should be connected. A trivial tree is a graph that consists of a single vertex. Why? Because if you have a single vertex, that vertex is connected, obviously, because there's only one vertex, and it is circuit-free because a circuit needs to have at least one edge. So since there is no edge in this graph, you can safely claim that the graph is circuit-free. So as a result, a graph with only one vertex is a tree. Then we have another definition which defines a forest. We say a graph is called a forest if and only if it is circuit-free and not connected. Why do we call it a forest? Because if a graph is circuit-free but not connected, it is composed of a number of connected components, right? A graph that is not connected has more than one connected component. Each of those connected components will be circuit-free, obviously, because the whole graph is circuit-free. So all of the connected components are circuit-free. So each connected component creates a tree. So the whole graph is a collection of trees, which we call it a forest.